Hello everyone from Learning Academy Foundation. I'm Mr. Andrea Filippo Lombardo, the founder of this educational beast for every class, for every grade, every subject. Today we are going to talk about representation of numbers in computer science. Okay, so the memory of computers has millions of switches, and any switch can be on, that its value is 1, or off with the value that is 0. The value of each simple digit is given by its position. The value is expressed in powers of 10 if it is in base 10. So 122 in base 10 is 1 times 10 squared plus 2 times 10 power 1 plus 2 times 10 power 0. That is 100 plus 20 plus 2, so 122. An example for base 2. Let's try to express the number 5 from decimal number, base 10, in binary basis. The value of each digit is given by its position. The value is expressed in powers of 2. So 101 in base 2 is 1 times 2 squared, that is 4, plus 0 times 2 power 1, that is 0, plus 1 times 2 power 0, it is 1. So 4 plus 1 is equal to 5 in decimal number. I was doing the L.A.F video. Oh, okay. One possible representation. Sorry. So with 3 binary digits, we can represent 8 values or states from 0 to 7. With 1 byte equal 8 bits, we can represent the 2 power 8 equal 256 values. Possible representation is to use the bit leftmost, the most significant identified sign. So 0 is positive and 1 is negative. In reality, we don't use this obvious notation, but switch to binary choose complement notation. This is the procedure for the choose complement representation. Represent the binary number as an absolute value. Complete the number, complement the number. So once becomes zero, and zeros become 1, and add 1 to the complementary number. So for example, we represent negative 5 in base 10 in choose complement. So first represent the binary number as an absolute value. So negative 5 in decimal base 10 is equal to absolute value of 5. In base 10 it is equal to absolute value of 0, 0, 0, 0, 0, 1, 0, 1 in base 2. Then complement the number. So the 1 becomes 0 and the 0 becomes 1. So 0, 0, 0, 0, 0, 1, 0, 1 in base 2 is, if we complement the number, becomes 1, 1, 1, 1, 1, 0, 1, 0 in base 2. and then add 1 to complementary numbers. So 1, 1, 1, 1, 1, 0, 1, 0, this 2 plus 1 this 2 is 1, 1, 1, 1, 1, 0, 1, 1 in base 2. So we can say that negative 5 in base 10 is equal to 1, 1, 1, 1, 1, 1, 0, 1, 1 in base 2. Positive and negative numbers can be added together following the rules from normal addition, regardless of the sign. So why we use this representation? First reason, because the computer can add two integers together without checking the sign, and circuit design is simpler as it requires just another circuit. Which are the encodings used to represent data? Characters made up of 26 capital letters, 26 lower capital letters from capital letter A to capital letter Z, 26 lowercase letter from lowercase a to lowercase z, 10 digits from 0 to 9, various symbols like the brackets or the question mark, the exclamation mark, the percentage symbol, the hashtag symbol, the operator symbol like plus, minus, etc. Thank you, Jane. Special letters and symbols, for example, letters with accent or the serie, the symbol of euro, symbol of dollars, and then natural numbers, whole numbers, and real numbers. We are going to talk about this one by one. Starting from the character encoding. So we know that 1 byte is equal to 1 character. In fact, we have seen how with 1 byte it is possible to express 256 different states. It was necessary to adopt a coding system that standardized natural number character correspondence. The coding systems are ASCII, American Standard Code for Information Interchange. This defines which characters are associated with the first 128 numeric values. ABCDIC, Extended Binary Code Decimal Interchange Code that now is in disuse, and Unicode for language that use more than 256 characters, use 2 bytes for character. The natural numbers are memorized exactly. They don't require the sign bit. They are mainly used to represent addresses of memory. 2 bytes or 16 bits equals addresses between 0 and 2 power 16 minus 1. 4 bytes, so 32 bits, is equal addresses between 0 and 2 power 32 minus 1. 8 byte, that is 64 bits, addresses between 0 and 2 power 64 minus 1. So since they are only positive numbers, arithmetic is not used of the complement of 2. When numbers are also memorized exactly, so the integers are made of positive and negative numbers plus 0. Generally, 4 bytes is equal to 1 integer. Not all numbers can be represented, but only those between negative 2 power n minus 1, that is negative 2,147,483,748 in base 10, and 2 power negative power n minus 1 that is equal to 2,147,483,747 in base 10, where the n is the number of bits, so it's equal to 4 times 8 equal to 32. Real numbers are numbers that cannot be represented with natural numbers. So for example, very large numbers like seconds, centuries, for example, 3,155,760,000, or very small numbers like an atomic diameter, that is 0.0000001, or rationals 2 over 3, rationals are the same or periodicals like 0.666666 periodical, irrational square root of 2, that is equal to 1.414213562373, etc. Transcendental, you play raw number, that is 2.7818, etc., or pi, that is 3.141, etc. In this case, scientific notation is used. How to represent the real numbers? So we have the sign of the mantissa that can be negative or positive before the number, and then the decimal point. After the decimal point, there is the one that is called mantissa times the power of the base of the base 10, for example, a sign of the exponent, in this case negative, and the exponent, in this case 6. So normalized meets the condition that the absolute value of the mantissa is between the base power -1 included and 1. So for example, in a not normalized real number 60.2 times 10 power 22, when normalized, becomes 0.602 times 10 power 24. For the binary number, the scientific notation is the same. So we have the sign of the mantissa, in this case is positive 1. The number before, the number after the mantissa is 1, and the decimal point is called flotation point, floating point, and the mantissa, that is in this example is 0.1010101 times the base 2 power the sign and the exponent, so 2 power 6. So the position of the track point is not fixed. For this reason, this representation is called floating point. In single precision, a real number is stored in 32 bits, of which 1 is used for the sign, 23 for the mantissa, and 8 for the exponent. I can then store real numbers that belong to this interval between 2 power -128 and 2 power 128 in base 2, then 10 power -38 and 10 power 38 in base 10. Approximate representation of the number, 7 significant digits in decimal representation. So we have the sign, exponent, sign, the exponent, and the mantissa, and the variable 1 of the floating point, and variable 2. For the fixed point, shared exponent 101, variable is 0.0110101, and the second variable. So as I said before, approximate representation of the number is 7 significant digits in the decimal representation. Can be overflow when number is too large, so greater than 1038. I cannot represent the exponent in 8 bits. greater than 10 power 38. I cannot represent the exponent in 8 bits. And underflow, when the number is too small, so greater than 0 or less than power greater than 0 and less than power negative 38. So the negative exponent is larger than that representable with 8 bits. What is the solution for this? We use multiple bits to represent the number. Double precision, I use 64 bits to store each number, of which 1 for the sign, 11 for the exponent, and 52 for the mantissa. So what is the difference between single precision and double precision? Single precision uses 32 bits, double precision uses 64 bits. Of these 32 bits in single precision, 23 are used for the mantissa, while in the double precision 52 bits of 64 are used for the mantissa. In single precision, the numbers are between 2 power negative 128 and 2 power 128 in base 2, while in double precision, the numbers are between 2 power negative 308 and 2 power 308 in base 2. Okay, for today is everything. I hope you have enjoyed the lesson. Please put like and subscribe to the channel so that you can follow the further lessons about computer science and about other subjects. And thank you for your attention. You can also follow the Learning Academy Foundation through the links of Facebook and Instagram that you will find in the description below. See you next time. Bye.